Alright, so we are on question 2 of the November 2018 South African Syllabus CAPS Mathematics Matric Paper 2. And we're on question 2, and it's another question on statistics. Now this question, you can say every question is just 1 mark, and most of this has to do with interpreting the data instead of actually doing calculations. So let's read and see what we have here. So a familiar question among professional tennis players is whether the speed of a serve in kilometers per hour depends on the height of the player in meters, and then they say the heights of 21 players and the average speed of their serves were recorded during a tournament. Data is represented in the scatter plot below, and the least squares regression line is also given. Okay, we can see this information here. Now question 2.1, let me write that down, 2.1. Okay, write down the fastest average serve speed in kilometers per hour achieved in the tournament. So that's something we can just read off, right? Here's the average speed for the tournament, and the fastest one is obviously the highest one, that one there. So all we need to do is read off that value. So we just go to the side, read off that value, and we see it's 250. Each little line is 1, right? So 251, 251 kilometers per hour. Kilometers per hour. That is the fastest one, and we can just read that off. Now question 2, 2.2. Let me change color for the next question. Let's do blue. So question 2.2, and then we've got a 0.1 and a 0.2. So consider the following correlation coefficients. So we've got an R. First of all, before we get to that, what is the correlation coefficient? Well, correlation coefficient is how good the two parts of the data correlate. So average serve and height of the player. How well are they correlated? So if we've got a line like this, right? This is our scatter plot, and then we draw a line through. That is obviously a very good correlation. You can see it correlates almost perfectly, right? Now, if we had something like this, let's say like that, so we can see there's not much correlation here. It's completely spread out, right? So if we draw a line of best, we don't even know if that's the line of best fit or if this is the line of best fit. So there's absolutely no correlation. So that would have an R of 0. A perfect correlation is 1. So if it goes like, actually, let's just redraw this quickly. So just back to the first one, if we've got something like that, so the line goes up and it crosses perfectly, that's a perfect correlation of 1. If we had a line like this, let's do another color for this one. If we had a line like that, going down, that would be an R of -1. Now notice that the R equals 1, R equals -1, that's not the gradient of the line. The positive and negative tell us the gradient, but we don't care if what the gradient is exactly. I mean, the line could be like this. That would still be R equals -1, because it's a perfect fit and the line is going down. Right, so that's the important thing. Now if we have something where the line is not a good fit, let's say something like that, or not a perfect fit, so that's a decent fit. I mean, we can at least see the trend, but there's a big distance between the line and the actual points. And so what we can see is the line still goes up, so we know it's going to be a positive number, but it's not going to be close to 1. It's going to be closer to 0. So maybe, let's say 0.3, something like that. Right, so if the line fits well with the dots, it's close to 1 or -1, depending if we go up or down. And if it's far away from 1 or close to 0, then the line does not fit the dots well. The dots are far away from the line. Alright, so that's the basic idea. Now let's see in this case. So consider these ones. So R equals 0.93. So what would this be? This is close to 1. So that would be a pretty perfect fit, right? The dots would be very close to the line and it would be going up. R equals -0.42. So for this one, the line would be going down and the dots would be pretty far away from it, right? And in this one, R equals 0.52. The line would be going up, but the dots would be pretty far away from it. Okay. Now they ask us which one of the given correlation coefficients best fits the plotted data. Okay, so we can see here the line goes up and the dots are quite far away from the line. So we're going to have to pick C. So C, or we could say C or R equals positive 0.52, right? So this is what we'll have as our answer, and hopefully it makes sense as to why. We can see it's positive because the line's going up, and we can see the dots are not very good fit on the line. I mean, they're far away from the line on average. So then we have a an R that's not close to 1 or further away from 1. All right, 2.2.2. 2.2.2. So use the scatter plot and the least squares regression line to motivate your answer. Okay, so now all we have to do is we just have to explain why we said that. And we just did, right? We said that the points are quite scattered. Let's just say that. So points are the points or the data are quite scattered. Quite scattered. Or you could say fairly scattered. Fairly scattered. So this gives us, so this part tells us the correlation coefficient is not close to 1 or -1. And then the second part is the line or the slope. You can say the slope is positive, or you could say the line is going up, or any of that thing. So this gives us what the number is, so far from 1 or -1 because it's very scattered, and this tells us whether the line's going up or down, so whether it's positive or negative, the R. So those are the two parts we need to get, and that'll give us our 1 mark, so probably half a mark each. Question 2.3. Let's switch colors again. What color did we, let's start with this one, 2.3. Okay. What does the data suggest about the speed of a tennis serve and the height of the player? Okay, so if a correlation is good, so if R, let's say this, so if R is close to 1 or to -1, then we know it's a very good predictor. We can use that to predict, and it's a high correlation, right? So if in this case, if the dots are pretty close to the line there, then we could say, well, there's a great correlation because R was close to 1, and then we could say, well, the height of a tennis player does have big correlation or big impact on the serve of the speed. But in this case, our R is quite weak. It's far away from 1. So we can say there's no conclusive evidence that the height influences the speed of the serve. So we'll say something like that. So no conclusive evidence that the height of a player influences their serve speed, right, or has an impact on the average speed of the serve, something like that. Okay, or you could say it's possible but we're not sure yet, something like that, but it's definitely not conclusive. So I think this is probably the best line. Just say there's no conclusive evidence because R is quite far away from 1. If it was very close to 1 or very close to -1, you could say it definitely has an impact. So maybe let's just do this. So let's say R was 0.98, right? If this happened, then we would say, okay, the taller the player, the faster the average speed. What if R was -0.98? What if this happened? Well, then we would say the taller the player, the slower or the less the average speed will be. Because then it would have a negative correlation, right? Negative correlation. Everything fits perfectly, so it's a good predictor. So we could say, okay, the taller player has the shorter player has the faster serve, the taller the player, the slower the average serve. Okay, so that's obviously not going to be the case. It's just pretty common knowledge that if you're tall, it's quite likely that you get a faster serve. And we could say it's possible here in our case, but it's not conclusive because the data is quite scattered. All right, question 2.4. 2.4. The equation of the regression line is given as y equals, I'm just going to write that down, so y hat, we call it y hat instead. So y hat equals 27.02, 27.02 plus bx. Okay, so we know from a straight line, this is our y-intercept, and that is our gradient. And now they're asking, first of all, what is y-intercept, right? Y-intercept is where it just cuts the y-axis, so if we continue drawing the line this way, that would be our y-intercept. And that'll be 27.02 in this case. Right, so explain why, in this context, the least squares regression line cannot intersect the y-axis at 0 and 27.2. And so if we just look at this straight line equation, we would say, well, 0 and 27.02, that would be a point on the line. So why can it not be in this case? Well, let's look at what it means. What we're doing is we're finding the x values. The x values are the height of the player height, right? And the y values, or y hat values, that is the average serve speed average, sorry for this, average serve speed. Average serve speed. So why can x not be 0? Well, can a person be 0 centimeters tall? No. So that's what you'll say. So a person cannot be 0 centimeters tall. That's impossible. So the line can't go there, right? And it would be hilarious, a 0 centimeter tall person having an average serve speed of 27 kilometers per hour. But that is obviously impossible, so this cannot happen. So like I said, this question is more on the interpretation, just on what some of the things mean in statistics. Not a lot of calculation happening in here. Alright, but that was it for question 2. And if you've got any questions on how to interpret or what to write, please let me know in the comments, and we can discuss that. I'll see you again for question 3.